guys. We're talking about integers and radicals and exponents, okay? I'm going to refer to some things, and I'm going to say, you guys might remember this from last year. Or I might say, you should remember this from last year. If you don't, please don't sit there and think, oh my gosh, I can't believe I don't. It's okay, right? We're going through it again. I need you to ask questions if you have some. We're going to go through this together. And hopefully, by the end, you're thinking, okay, I can do this. One thing I do want to bring to your attention is we don't use calculators much in here. All right? Assume you can't use one until I say, go ahead and bring in a calculator. So like this first quiz, you are not using a calculator. Can I control what you do at home? No. But it doesn't do you any good to use a calculator on your homework, and then when it's time for the test or quiz, you're like, oh, wait, I can't do this. All right, when we first look at stuff, I call it in book talk, right? With all these letters and stuff, it kind of can get lost. I understand that. It can not make any sense to you. So I like to look at examples as much as we can that have numbers. It's easier to really wrap your head around what they're asking you to do here. In this first example, we're talking about properties of exponents. One of the first properties that we're going to talk about is when the bases are the same and you're multiplying the same bases, you add the exponents, right? What is the base in this first example? What's the base? What number? 3. Good. So this is saying 3 to the second times 3 to the fourth equals 3 to the 2 plus 4. So what this question would look like if you wrote it out is you would say 3 to the second, which is 3 times 3, times 3 to the fourth, which is 3 times 3 times 3 times 3, right? Well, how many 3's do I have there? 6. So this just proves the property that when you have bases that are the same and you're multiplying them, you simply add the exponents together. And then we're going to simplify. You always, always, always simplify. Even if it doesn't say simplify, you have to simplify your answer, which means give me the most simplified answer you can. When I have bases that are the same, and what are we doing here?
Subtract.
Right. We're going to subtract because what are we doing in this first example? It says x to the 7th, what? X to the 4th? Divided by. When you divide bases that are the same, you subtract their exponents. So in this case, it's 7 minus 4, because what this is really looking like is 7x's on top, 1, 2, 3, 4, 5, 6, 7, over the 4x's on the bottom. What's anything divided by itself? 1. So cross off 1 here, 1 here, 1 here, 1 here. I'm left with what?
1.
X to the what? 3rd, right? There's 3 of them. Okay? Simple enough. All right, what are we looking at here? What's the problem there? What kind of a 4 is that? Negative. We don't like negative exponents. A lot of times I like to say, in order to make a negative exponent positive, we move it through the fraction bar. Meaning, if it's in the numerator, you move it to the denominator. If it's in the denominator, you move it to the numerator. Well, in this case, you guys might say, well, there's nothing in the denominator. What is right under this y that we don't see? It's just understood.
1.
It's a 1. So what this is really saying is y to the negative 4th over 1. In order to make a negative exponent positive, you move it either from the numerator to the denominator or vice versa. So all they did was just take this, put it underneath, and it became positive. Does everybody see that? Okay, so like if I had this, if I had 2 over x to the negative 3rd, right? We don't like that. That's not simplified because you can't have negative exponents. So what should I do with this? I would move this up here, and it would become 2x to the 3rd. Everybody see that?
You can't drop the 2.
No, you would leave it there because it stays in the numerator. Right, good question. All right, this is a super duper important concept. If you ever get a problem like this on a test or a quiz, please don't mess this up. What is anything raised to the 0 power?
1.
Good. Anything raised to the 0 power is 1. Make a note of that, highlight it, whatever you need to do. In this case, we have something in a parenthesis raised to a power. Well, this power goes to everything inside of the parenthesis. If you had 10 variables in there, you would distribute that 3 to all 10 of the variables. And then you simplify accordingly. We can always simplify our numbers. So 5 to the third power gave us the 125. And then our x's just stay as x cubed. Everybody see that?
You did 5 times 5 times 5, right?
Yep, perfect. 5 times 5 is 25 times 5 would be 125. How did I get from here to here?
You multiplied by 3.
A power raised to a power, we multiply. Now, why is this right here not simplified? Y to the negative 12? How come I can't just leave it like that?
Because it's negative.
Because we don't like negative exponents, right? So how do I make a negative exponent become positive? Well, this is really over 1. So we move it down, and I get 1 over y to the 12th. Questions? All right, so let's look at a question like this. We have 2 over x raised to the third power. Well, remember, when you have a power outside of a parenthesis, you distribute to everything inside. So I'm going to distribute to the numerator and to the denominator. And when I do that, I can simplify 2 to the third power. What's 2 times 2 times 2? That's our 8. And then I just leave x cubed. All right, just a little review of our power stuff. So we're going to go through some examples, and then I'll go to your homework, and we'll look at some of your homework stuff. Kind of go back and forth. You guys will have homework tonight, but hopefully you can get some of it done while we're going through our lesson here. So let's go to the next page. All right. Anybody recognize this handwriting? It's Miss Glick's. It's Heron's. It's definitely not mine. Yeah. Anytime anything's written really pretty, it's because she did it. But what are we doing here? What are we doing with these two parentheses? We're multiplying. How do you know they're multiplying, Josh? Yeah, they're stuck together, right? There's no signs in between. All right, and then you can kind of look and you can say, all right, there's different pieces. Guys, I have to impress upon you enough. I like to give you credit on your tests and quizzes. I do. But you have to show me your thought process. The more you can show me, the more credit I can give you. Say you got down to the end here, and instead of telling me this was negative 12, A something, B something, you told me it was 7. What did you do? You added, all right? You just weren't paying attention. That's not that big of a deal if I can see your thought process. But if you don't show me any of your work, all you do is just write 7. I don't see that you just made a silly mistake, that you realize you were supposed to multiply, but you didn't, those sorts of things. So show me as much work as you possibly can. And I will give you as much credit as I possibly can. So here I'm just going to simplify. I have a negative 3 times positive 4. What does that give me? Negative 12, right? Now I have an A here and an A here. What is the power to both of those A's?
A to the second.
It is going to be A to the second, but individually, what is it? A to the what? A to the 1, right? You don't see it. It's A to the first power. You don't have to write the 1, but it is a 1. But if you notice, guys, we're multiplying two bases that are the same. So what do we do to the exponents? You add them. 1 plus 1 is 2. Good. Now I have b to the 4th, b to the negative 3rd. Same base. We keep our base the same, and we do what to our exponents? Add them. Good. What's 4 plus negative 1?
1.
Sorry. 4 plus negative 3? 1. Do I have to write the 1 on the b? No. So you can if you want to, but you would just leave it just like that. But do you see how I circled a little bit? I wrote the little ones. I underlined the negative 3 and the 4. That's you guys showing me some work. Let's look at the next one. What jumps out at you? The 0. That whole parenthesis is raised to the 0 power. So I can just cross that out and make it a what?
1.
Good, because anything raised to 0 power is 1. So I have 3a times 1 gives me 3a. Please, guys, if I give you a layup like that, don't miss the shot. You're not even covered on that. Like, nobody's around you. Do you guys understand that? I know you do. All right, look at the next one. How's this one a little different? Or do we have the same bases being multiplied together? No. What do we have? We have an exponent. We have a whole parenthesis and it's raised to a power, right? So that means this 3 is going to go to the 2. Good. We're going to distribute to the x and to the y. So I have 2 to the 3rd power. Then I have x to the 3rd power. And I have y to the what?
Six.
6. Good. If you raise a power to a power, we multiply. If it's the same base, you add them together. But if it's a power raised to a power, you multiply. Is this completely simplified?
No.
No. If this was a 10-point question and you left it like this, I'd probably give you 8 points. Why would I take 2 points off?
Because you didn't simplify enough.
Yep. What else can you simplify?
The 2 to the third.
2 to the third is what?
8.
2 times 2 is 4 times 2 is 8. Remember, it's 2 times itself 3 times. So it's 8 x cubed y to the 6th. Good.
That's it.
Mm-hmm. That's the most you can do. Now we go here, and you're like, ooh, there's a lot going on. Not really. We have a parenthesis, and it's raised to a power, yes? So what do I do with this power? I'm going to distribute it to everything. Good. Top and bottom. So I have 5 squared. I have x. I'm raising a power to a power. So what do I do with the 3 and the 2? Multiply. Good. 6. Then I have y squared. Completely done?
No.
Nope. What can I do?
Can you simplify the exponents?
5 squared would be what? 25. And then I have x to the 6th, y to the 2nd. Now, when you say simplify the exponents, because we're dividing, you're thinking, oh, I could subtract or something, right? But are the bases the same? No. So x stays x, y stays y. Now we're going to talk about radicals and stuff like that, radicals and their properties, okay? You guys have seen radicals before. You've seen square root a lot. Okay, we're going to talk about roots, whether it's an even root or an odd root. What's an even number? 2, 4, 6, 8. Good. What's an odd root? 3, 5, 7. Perfect. So we got it. That's good. If you are talking about perfect squares, I'm going to refer to perfect squares a lot. These are our first few perfect squares. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared 16. 5 squared 25. 6 squared 36. You guys should know at least up through 15, just off the top of your head. If you don't, it's okay, but you should know those. When we talk about perfect cubes, guys, that's a number multiplied by itself 3 times. So 1 cubed is 1. 2 cubed is how much? 8. 2 times 2 is 4 times 2 is 8. 3 cubed, 4 cubed, 5 cubed. Numbers get bigger in a hurry, right? So you are going to have to think in terms of cubes. We're going to get to our imaginary complex numbers in a little bit, but we should remember that the square root of a negative number is not real. It's going to give us the I in our answer, but we're not talking about that right now. So let's go and look at some cube stuff. Same kind of rules apply. Same kind of rules apply. If you are asked to simplify, like in a question like this, this is saying the cube root of 8 squared. You can square 8. 8 times 8 is 64. Then figure out what times what gives you 64. Or you could take the cube root of 8, which what number times itself 3 times gives you 8? It's 2. And then 2 squared is 4. You'd get the same answer. So you're going to have to do a little bit of problem solving and some thinking. And we're going to go through a couple examples like that in a second. This second property right here, it's the square root of 5 times the square root of 7. How do you know that's the square root? Because of the thing, right? How do I know this is the 4th root? Because there's a 4. So what number is right here that we already know it's there, we just don't write it? Not a 1, the 2. That's what the square means. So these are the same indexes. That little number in the front is called an index. So I always say the same houses you can combine. A house times a house is a bigger house. What I mean by that is, look, it's the square root of 5 times the square root of 7. Well, we can simplify that into one radical. 5 times 7 gives me the square root of 35. If it was the cube root times the square root, you can't. But if they're the same index, which is the little number in front, you can combine them.
So they're the same unless they put a different.
Like same odd or even?
No, like exact same number.
Oh.
Like 2, 3, 4. Like this, the next example, 4 through to 27 over to 4 through to 9. They want you to just simplify. They want you to make it smaller. Is there a number that you can multiply by itself 4 times to give you 27? No.
No.
Is there a number that you can multiply by itself 4 times to give you 9? No. But are they both the same index? So those two little houses, you can put them under the same house because they're dividing. When you do that, can you simplify 27 divided by 9? 3. That's where that 3 came from. All right, when we talked about a power raised to a power, like 5 squared to the 3rd power, what do you do with these two powers if it's a power raised to a power? We multiply. Same thing here. This is a radical inside of a radical. What's this little number right here that we don't see? 2. So how did they go from the cube root of the square root of 10 to the 6th root of 10? They just multiplied here. That's it. And here's the nifty little thing that we love. What do you guys notice here? It is in parentheses. Good. What else? This is squared. Good. What's the number right here? It's an invisible 2. So when you square a square root, when you cube a cube root, when you take the 4th power of a 4th root, what do they do to each other? They cancel out. Good. So this becomes just a 3. That make sense? Okay. So let's do a couple and then we'll go to your homework. All right, let's just think for a second. We need to simplify, all right? There's not a roadmap that you do the same thing every time. You got to look at each question separately and say, okay, what's my plan of action? So I look at this. Do I know the square root of 8 off the top of my head? No. Do I know the square root of 2 off the top of my head? No. But they're both square roots, right? So a house times a house is just a bigger what? Yeah, so I can rewrite this as the square root of 8 times 2. Let me see if that helps anything. What is 8 times 2? 16. Do you guys know what the square root of 16 is? Good job. Perfect. So I'm not looking for the answer of 4. I'm looking for the whole process that you understood. You can combine those two radicals. Then once you combine the two of them and multiply, then you can simplify to a whole answer. All right, let's look over here. Anybody?
It cancels.
Why?
Because there's a 3.
Yep, because there's a cube root and it's to the 3rd power, so that cancels out. I'm left with just plain old x. Good.
Can x have like in parentheses?
You can. That's fine. What about this? What's my answer? 5. Good. What's my answer here? Y. Good job, guys. Good. Do you want like 12 of those on your quiz?
Yeah.
Bunch of those and everything raised to the 0 power, right? All right, let's go. Let's do this one. We're cube root of 24. I don't know any number that's going to multiply by itself 3 times, give me 24. But what's a cube that's inside of 24? 8. Good. We can break this up into 8 times what? 3?
Yeah.
Okay, what's the cube root of 8?
2.
So this comes out, becomes 2 times the cube root of 3. Now, please, guys, my handwriting is not good. But make sure that I understand that your answer is 2 times the cube root of 3, and it's not like 23 root 3. Right? Those two things are very different. So make sure if your number is supposed to be little, keep it little. If it's supposed to be big, keep it big. Understand? All right, let's come over here. The 4th root of 48. So is there a number times itself 4 times that's going to give me 48? No.
12.
Okay, 12 times what?
4.
All right. Are either of those cubes, though? I mean, 4th roots?
No.
Okay, what's another? How else can I break this down? Ooh, what do I hear? 16 and 3. Good. Very good. What times what? Times what times what gives me 16? 2. 2 times the 4th root of 3. Remember, it's not 24 root 3. I guess gotta do a little bit of thinking. All right, how about this? We'll do this one and then I have one more example to do. This is the square root of 75x cubed. Square root. Square root. What's the little number that's there? It's a 2. What can we break 75 into that has a perfect square in it?
25.
Yep, 25 times 3. And then how many x's do I have? 3. I have 1, 2, 3. So what is the square root of 25? So 5 comes out. How many in a group? How many x's do I have to have in a group before I can pull it out? Here's one group of 2 that I'm going to pull out. So I write it here. And now what's left over? Perfect. Good job, guys. Good. I pulled out one group of 2. You have a question or no?
No, I just said I got it right.
Okay. Good deal. Good deal. All right. What's the answer here? Yes, good. Very good, very good. Remember, don't get confused on those. All right, I want to do these last 2. And then there's only one on your homework that you guys won't be able to do. And we'll do that tomorrow. But you can do everything else. What do you notice about this problem? Talk to me.
Subtracting.
Okay, it's subtracting 2 radicals. If I said to you, this was like 2x minus 3y, could you combine these? No, because they don't have what? They don't have common terms, right? We'll say last names. X and Y are their last names. When you have radicals that have different radicals, under different numbers underneath, as long as the index is the same, that little number in front, you can break them down to see if you can make them to be the same. 95% of the time it's going to work. So what I'm saying by that is we're talking about square roots here, right? So I have 2 times, break down 48. What can I break down 48 into that has a perfect square and a non-perfect square? 48. Mm-hmm. 12 and 4, but there's perfect squares in 12 and 4.
6 and 8.
6 and 8, but there's a perfect square in 8, and then you have to pull it out more. Think a bigger number. We've already had, you're going to start to see repeats. We've already had 48. What do we break 48 into? You told me. 16 and what? 16 and 3. That's the biggest perfect square and the smallest non-perfect square. That's what you're going for. Now I'm going to say minus 3 times. Well, what can I break 27 into? A perfect square and a non-perfect square. 9 times 3. All right, is everybody with me? What do you notice now? They both have a 3, right? When I simplify this, what is the square root of 16?
4.
So this 4 comes out. So I have 2 times 4, which is 8. Square root of 3. Minus, what's the square root of 9? So I have 3 times 3 is 9. Square root of 3. How about that? Do they now have the same last name, same common radicals? What's 8 of something minus 9 of something? -1. So this would be -1 square root of 3. You won't see the -1 written there. You'll just see it like this. But if you wrote the -1, that's fine. But I promise you, about 90% of the time, if I give you a problem like this that has 2 different radicals or 3 different radicals and it says combine, you'll be able to combine them so they all have the same common radical, and you'll be able to get a more of a simplified answer. This one's the same concept. It's just now it's a cube root and has letters, but that's okay. Let's think about 16 and breaking up into something that has a perfect cube in it. Well, 16, we've talked about 16 already a bunch. What's 16 break up into? 8 and 2. Is 8 already a perfect cube? Yes, we've talked about this already. Now minus, I have 3. What about 54? Okay, 6 and 9, I agree. 6 and 9 is good, but I think we want to have the common radical, right?
7 times 8.
Not 7 and 8. Think bigger. Think a bigger perfect cube and a smaller non-perfect cube. Ooh, who said that? 27 and 2. How many x's are there? 9's a perfect square. There's 4 x's, right? Perfect cube means the number times itself 3 times. So a perfect cube, the cube root of 8 is 2. So this gives me 2 times the cube root of 2x. What's the perfect cube in 27?
9.
Not 9. 3. Good. Remember, it's times itself 3 times. So 3. And then how many groups can I take out of 3? I can take out one whole group. Good. And then what am I left with? There's a 2 underneath there and the x, right? Can I combine any more? Do they both have the same radicals now? Yes. But can I combine them any more than this?
No.
Why not? Because this is a 2 and this is a -3 with an x. So this would be it. But you did break it down so they had the same common radical at the end. All right?